Hello everyone, welcome to our presentation. Today we're going to explore acids, bases, and salts. This is an exciting topic in chemistry that helps us understand the properties and reactions of different substances. Over the next few slides, we'll cover the basics, their characteristics, and how they interact. I'm glad you're here, so let's get started. Let's move on to slide 24, which is about bleaching powder. Bleaching powder is a chemical compound commonly used for whitening and disinfecting. It's also known as calcium oxychloride and is widely used in households and industries for cleaning, bleaching clothes, and sterilizing surfaces. Its strong oxidizing properties help kill germs effectively. Understanding bleaching powder helps us see how chemicals can be applied in everyday life for hygiene and safety. Now, let's see how it fits into the broader topic of chemicals and their uses. Welcome to our next topic, what is an acid? Today, we're going to explore the fundamental concept of acids, which are essential in many chemical reactions and everyday substances. First, an acid is a substance that can donate hydrogen ions, or protons, in a chemical reaction. This ability to release protons makes acids taste sour and often causes them to react with metals and other materials. You'll find acids everywhere. Think of citrus fruits like lemons and oranges, which contain citric acid. In the broader context of our presentation, understanding acids helps us grasp how they interact with other compounds, which is crucial in fields like chemistry, medicine, and environmental science. So, as we move forward, keep in mind that acids are not just corrosive or sour substances. They're fundamental to many processes that shape our world. Let's take a moment to understand what a base actually is. When we talk about bases, we're referring to substances that can accept hydrogen ions or, more generally, donate electron pairs. Think of bases as the opposites of acids. They often have a bitter taste, slippery feel, or feel soapy. In many chemical reactions, bases play a crucial role because they help neutralize acids, balancing out pH levels. Recognizing what makes something a base helps us understand many processes, from biological systems to industrial applications. Connecting this to our overall theme, understanding bases is essential because it allows us to grasp how substances interact, react, and influence the environment around us. Let's take a closer look at the physical properties of acids and bases. Starting with color, mineral acids are typically colorless, which makes them quite different from organic acids, which usually appear as white solids. When it comes to bases, they are generally also colorless, but there are exceptions, specifically with hydroxides of iron and copper, which can have distinct colors. Now, moving on to taste, acids are known for their sour flavor, which you might notice in lemon or vinegar. Bases, on the other hand, tend to taste bitter, like baking soda or soap. Regarding touch, acids don't really have a specific tactile sensation, but bases often feel slippery or soapy to the touch, which is a quick way to identify them in many cases. Finally, solubility is an important property. Most acids are soluble in water, which is part of what makes them so reactive. Bases can also be soluble, and when they are, we often refer to them as alkalis. Some bases are soluble while others are not, so this property can vary. Understanding these physical properties helps us distinguish acids from bases and connects to their chemical behavior, which is essential in many practical and industrial applications. Let's take a closer look at how acids and bases react with metals. When a metal reacts with a base, such as a metal hydroxide, it produces a salt and hydrogen gas. For example, if we have sodium hydroxide reacting with zinc, it forms sodium zincate and releases hydrogen gas. Similarly, when an acid reacts with a metal, the metal displaces the hydrogen from the acid, forming a salt and releasing hydrogen gas as well. A good example is magnesium reacting with hydrochloric acid, which results in magnesium chloride in solution and hydrogen gas bubbling up. The key point here is that metals can displace hydrogen from acids, and alkalis, being soluble bases, also react with metals to produce salts and hydrogen gas. This process is fundamental because it highlights how reactive metals are with acids and bases, and it ties into the broader theme of chemical reactions involving different types of compounds. Let's take a closer look at how metal carbonates and bicarbonates react with acids. When these compounds come into contact with acids, they produce a salt, carbon dioxide, and water. For example, sodium bicarbonate, or NaHCO3, reacts with hydrochloric acid, HCl, to form sodium chloride, CO2, and water. Similarly, sodium carbonate, NaCO3, reacts with HCl to give 2 molecules of sodium chloride, along with carbon dioxide and water. An important point to remember is that bases do not react with metal carbonates or bicarbonates at all, so this reaction is specific to acids. This reaction is key because it explains how carbon dioxide is released during these processes, which is relevant to many applications, from baking to environmental science. Overall, metal carbonates and bicarbonates react with acids to produce these essential components: salt, CO2, and water, and this reaction helps us understand their behavior in different chemical contexts. Now let's look at how metal oxides react with acids. When a metal oxide reacts with an acid, the products formed are a salt and water. For example, calcium oxide, which is a solid, reacts with hydrochloric acid, an aqueous solution. The reaction produces calcium chloride, which is a salt, and water. This process highlights that metallic oxides are basic in nature, meaning they tend to react with acids to form salts and water. This is an important concept because it connects the basic properties of metal oxides with their ability to neutralize acids and form salts, fitting into the broader theme of acid-base reactions. Now let's look at how nonmetal oxides interact with bases. When a nonmetal oxide reacts with a base, the overall reaction results in the formation of a salt and water. For example, consider the reaction between sodium hydroxide, NaOH, and carbon dioxide, CO2. This reaction produces sodium carbonate, NaCO3, along with water. It's important to remember that nonmetal oxides are generally acidic in nature, meaning they tend to react with bases. When they do, they neutralize each other, leading to the formation of a salt and water. This process highlights the neutralization reaction, which is a key concept in understanding acid-base chemistry. Connecting this to the broader theme, these reactions illustrate how acids and bases, including nonmetal oxides, interact to form salts, emphasizing the importance of understanding chemical reactivity in different contexts. Now let's look at a typical neutralization reaction. When an acid reacts with a base, they combine to form a salt and water. For example, when sodium hydroxide, which is a strong base, reacts with hydrochloric acid, a strong acid, they produce sodium chloride, which is our salt, and water. This process is called a neutralization reaction. It's important because it explains how acids and bases essentially cancel each other out, resulting in a more neutral solution. Understanding this reaction is key to many practical applications, from industrial processes to everyday chemistry. It highlights the fundamental relationship between acids and bases and how they interact to produce neutral compounds. Now, let's explore the different types of indicators. First, we have olfactory indicators. These are quite interesting because their odor changes when they are in acidic or basic media. For example, vanilla or onion, they give off a distinct smell depending on the pH of the solution they are in. This change in smell helps us identify whether a substance is acidic or basic. Next, we have synthetic indicators. These are man-made and synthesized in laboratories. They are highly specific and reliable for testing pH. Examples include methyl orange and phenolphthalein. These indicators change color at particular pH levels, making them very useful in laboratories for precise measurements. Then there are natural indicators. These are derived directly from nature, which makes them eco-friendly and accessible. For instance, litmus, which is obtained from lichens, and turmeric, a common household spice. These natural indicators also change color depending on whether the solution is acidic or basic. To summarize, there are 3 main types of indicators: olfactory, synthetic, and natural. They all serve the same fundamental purpose: to tell us whether a substance is acidic or basic by changing their color, or, in some cases, their smell. This helps us understand the nature of various substances in a simple and effective way. Alkalis are quite fascinating because they give a characteristic color to the flame when you burn them, which is a useful identification feature. They can also be stored easily in mineral oil solutions, which helps prevent them from reacting prematurely with moisture or air. One important thing to remember is that alkalis have low melting and boiling points, making them relatively easy to melt and vaporize compared to other substances. They are highly reactive, especially with halogens, which are elements like chlorine, bromine, and iodine. This reactivity is a key point because it shows how alkalis can easily form compounds with these elements. In terms of physical properties, alkalis tend to be soft and have low density. This softness means they can be easily cut or shaped, and their low density makes them lighter compared to many other materials. Now, when we talk about their properties, one important measure is pH. Alkalis have a pH greater than 7, indicating their basic nature. An alkali is essentially a type of base that dissolves in water, forming alkaline solutions. These solutions are often soapy to the touch, which you might notice if you've handled soap or cleaning agents containing alkalis. They also tend to be bitter and can be corrosive, so safety is always important when handling them. For example, common alkalis include sodium hydroxide, NaOH, and potassium hydroxide, KOH. These are widely used in industry and laboratories, highlighting their importance. So, to sum up, alkalis are bases that dissolve in water, are easily identifiable by their characteristic properties, and play a vital role in various applications due to their reactivity and physical traits. When we talk about dilution, we're referring to the process of mixing an acid or base with water, which results in a decrease in the concentration of ions, specifically H3O+ or OH, per unit volume. This is an important concept because it helps us control the strength of acids and bases in various applications. Now, when adding water to concentrated acids, such as sulfuric or nitric acid, it's crucial to remember that this process is highly exothermic. That means it releases a lot of heat rapidly. If water is added too quickly, the heat can cause the mixture to splash out, which can lead to burns or injuries. Additionally, the container holding the acid might even break due to the sudden temperature rise. To prevent accidents, the proper method is to always add acid to water, not the other way around. This way, the heat disperses more safely. And of course, constant stirring is necessary to ensure the heat is evenly distributed and to avoid localized overheating. In summary, always add acid slowly to water with continuous stirring, especially with concentrated nitric or sulfuric acid. This careful approach helps us manage the heat generated during dilution and keeps the process safe. All right, let's dive into the pH scale. When the value is more than 7, we're looking at a basic or alkaline solution. If the value is less than 7, then it's an acidic solution. The perfect balance point is exactly 7, which indicates a neutral solution, like pure water. Now, the pH scale itself ranges from 0 to 14. On the lower end, around 0, the solution is very acidic, and on the higher end, around 14, it's very alkaline or basic. You might wonder what the P in pH stands for. Well, in German, Potenz means power, which is what the pH measures, the power or concentration of hydrogen ions in a solution. This scale was developed specifically to quantify how acidic or alkaline a solution is by measuring the concentration of hydrogen ions. And to tie it all together, the pH scale is a universal way to understand the chemical nature of a solution, whether it's used in lab testing or in everyday life. So, by understanding the pH, we get a clear picture of how solutions interact with our environment and each other. The survival of aquatic life in such rivers becomes increasingly difficult when acid rain flows into them. You see, when acid rain enters a river, it causes the pH of the water to decrease. And this drop in pH can be quite harmful to the organisms living there. Now, if the pH of rainwater falls below 5.6, we call that acid rain. Living organisms, whether they're plants or animals, can only survive within a narrow range of pH levels. For example, our own bodies function best within a pH range of about 7 to 7.8. That's a pretty tight window, and it highlights how sensitive living things are to pH changes. So you might wonder, are plants and animals pH sensitive? Absolutely, yes. Changes in pH can affect their growth, reproduction, and overall health. This is a critical aspect of our environment and ties into the larger theme of how human activities impact ecosystems. Understanding pH in our everyday life helps us see the importance of maintaining natural balance for the health of all living beings. The change in pH of the soil really impacts how well plants can access the nutrients they need for healthy growth. If the soil is too acidic or too alkaline, it can make certain nutrients either unavailable or toxic to plants. So, it's essential that the soil remains within a balanced pH range. Ideally, the soil should not be too acidic or too alkaline. When the pH is just right, plants can absorb nutrients effectively, leading to healthier growth. The optimal pH range for most plants is between 5.5 and 7. Within this window, nutrients are most available, and plants can thrive. Different plants require different pH levels for their ideal growth, which is why understanding and managing soil is so important. So when we ask, what should be the pH of soil in the backyard? The answer is, it should be maintained within this optimal range to support healthy, vigorous plants. Proper soil ensures your garden remains lush and productive. To neutralize the excess acid in our stomachs, we often use magnesium hydroxide, commonly known as milk of magnesia. It works by balancing the pH and reducing that burning sensation we feel with acid indigestion. To get rid of pain caused by too much acid, people turn to bases called antacids. These help quickly alleviate discomfort by neutralizing the stomach acid. Now, during indigestion, the stomach tends to produce an excess of acid, which leads to pain and irritation. That's why managing acid levels is so important for comfort and health. Interestingly, our stomach naturally produces hydrochloric acid, or HCl. This acid is essential because it helps break down food efficiently without damaging the stomach lining itself. So a key question is, what is the pH in our digestive system? Well, the stomach's pH is usually quite acidic, around 1.5 to 3, perfect for digestion, but needing regulation to prevent discomfort. Understanding this balance helps us appreciate how our body maintains a healthy environment for digestion, and why we sometimes need remedies when things go off course. The best way to prevent tooth decay is by cleaning the mouth regularly with basic toothpastes. Bacteria that naturally live in our mouth produce acids when they break down sugars and food particles left after eating. This acid production is what causes trouble. When the pH level in our mouth drops below 5.5, these acids start to corrode the tooth enamel. And it's important to remember that tooth enamel is made up of calcium hydroxyapatite, which is actually the hardest substance in our entire body. So, tooth decay begins when the pH in the mouth falls below that critical 5.5 level. This shows just how important maintaining a neutral or slightly alkaline pH is for protecting our teeth. In essence, yes, pH change is directly responsible for tooth decay. Keeping the mouth's pH balanced helps prevent the acids from damaging the enamel and keeps our teeth healthy over time. Now let's talk about the stinging hairs of nettle leaves. When they come into contact with skin, they inject a chemical called methanoic acid, also known as formic acid. This causes a burning pain that can be quite uncomfortable. Interestingly, applying a mild base like baking soda to the affected area can help provide relief from this pain. Similarly, some leaves, like those of the bee-stinging plant, contain acids that cause pain and irritation when touched. These are examples of how plants, just like animals, have developed chemical defenses to protect themselves from threats. This ties into the broader theme of our presentation. how both animals and plants use chemical warfare as a form of self-defense. These natural strategies are fascinating because they show the ingenious ways living beings protect themselves in their environment. Now, let's look at some naturally occurring acids that we find in everyday life. For example, vinegar contains acetic acid, which gives it that distinctive sour taste. Or take oranges. These are rich in citric acid, which is responsible for that tangy flavor. Tamarind is another interesting one. It contains tartaric acid, contributing to its unique sourness. Tomatoes have oxalic acid, which, while less noticeable in flavor, plays a role in the plant's chemistry. Curd, or yogurt, contains lactic acid, which not only adds to its taste but also helps in fermentation. Lemons are well known for their high citric acid content, making them super sour and refreshing. Interestingly, even some stings from ants and nettles involve methanoic acid, also called formic acid, which causes that burning sensation. These examples highlight how natural sources provide a variety of acids that influence flavor, texture, and even plant or animal defense mechanisms. This connection between nature and acids really ties into our overall theme of understanding the role of acids in our world. All right, so when we talk about salts, we're referring to a specific type of compound formed when an acid reacts with a base. These are not just the table salt we use in cooking, but a broad category that includes many different substances. Salts are essential in many biological and chemical processes because they help maintain balance in our bodies and in the environment. Key points to remember are that salts are typically crystalline solids, and they consist of positive and negative ions held together by ionic bonds. This structure gives salts their characteristic properties, like high melting points and solubility in water. Connecting this to the overall theme, understanding what salts are helps us grasp their role in everything from nutrition and medicine to industrial applications. They are fundamental to both natural processes and human-made technologies, making them a crucial concept to understand in our study of chemistry and life sciences. Let's talk about common salt, or sodium chloride, which is truly a fundamental substance in many industries. It serves as a major raw material in the industrial manufacturing of various chemicals, such as sodium carbonate and sodium hydrogen carbonate. These chemicals are essential in a wide range of applications, from manufacturing to cleaning products. Salt is also incredibly important in the food industry, where it is widely used as a preservative to keep food fresh and safe for longer periods. You might be surprised to learn that the simple act of salting food has such a big impact on food preservation. Now, in terms of its uses, one key chemical reaction involves hydrochloric acid and sodium hydroxide reacting to produce sodium chloride and water. This reaction highlights how salt can be produced through a straightforward chemical process. The preparation of sodium chloride is quite simple. It results from the combination of HCl and NaOH, which are common acids and bases used in various chemical processes. Its chemical formula is NaCl, and as we see, it's also known as sodium chloride, which is its chemical name. So, in summary, common salt is more than just a seasoning. It's a vital industrial and commercial resource that plays a crucial role in manufacturing, preservation, and chemical production, linking back to our overall theme of the importance of fundamental substances in industry. Let's talk about caustic soda, also known as sodium hydroxide with the chemical formula NaOH. It's a very versatile chemical used in many industries. For example, it's used for degreasing metals, which is essential in manufacturing and maintenance to ensure surfaces are clean and ready for further processing. Additionally, caustic soda plays a crucial role in making soaps and detergents, as well as in the production of paper and fibers. These applications highlight its importance in everyday life and industrial processes. Now, you might be wondering how it's made. It's produced through a process called the chloralkali process. Basically, when electricity is passed through an aqueous solution of sodium chloride, or brine, it decomposes into sodium hydroxide, chlorine gas, and hydrogen gas. This process is fascinating because it efficiently produces several key chemicals simultaneously. So, to sum up, caustic soda is essential in cleaning, manufacturing, and many chemical processes, making it a cornerstone chemical in industry. Let's talk about bleaching powder and its many uses. It is also used as an oxidizing agent in various industries, which makes it quite versatile. One of its important applications is in making drinking water germ-free, helping to ensure safe and clean water for everyone. The chemical reaction involved is Ca, O2 reacting with Cl2 to produce Ca-Alkyl2 and H2O. Now, how is it prepared? It's formed by the action of chlorine on calcium hydroxide, which results in the production of calcium oxychloride, known as bleaching powder. Its chemical formula is Ca-Alkyl2, and the chemical name is calcium oxychloride. Overall, bleaching powder plays a crucial role in sanitation and water treatment, connecting to our broader theme of chemical applications for health and safety. Now let's talk about baking soda, which has quite a few interesting uses. One of its common applications is in soda acid fire extinguishers, where it helps put out fires effectively. It's also a kitchen staple, used in making crispy pakoras, giving them that perfect texture. Chemically, baking soda is sodium hydrogen carbonate, with the formula NaHCO3. It's produced through a reaction involving common substances: sodium chloride, water, ammonia, and carbon dioxide. When these react, they form baking soda along with ammonium chloride as a byproduct. So, whether it's in firefighting or cooking, baking soda's versatility really shines through. It's a great example of how chemistry connects to everyday life, making our routines safer and more enjoyable. Washing soda, which is chemically known as sodium carbonate decahydrate, has quite a few practical uses. One of its common applications is as a cleaning agent in our homes. It's especially useful for removing tough stains and grease, making cleaning more effective and easier. Another important point is that washing soda helps in removing the permanent hardness of water. Hard water contains minerals like calcium and magnesium, which can cause issues like soap scum and scale buildup. By using washing soda, we can soften the water and improve the efficiency of cleaning and laundry processes. Now let's look at how it's prepared. The key reaction is NaHCO3 combining with water molecules. When 10 water molecules are added to sodium carbonate, it forms this hydrated compound, which we call sodium carbonate decahydrate. Its chemical formula is NaHCO310H2O. This formation is significant because the decahydrate form is more stable and easier to handle in various applications. So, whether you're cleaning or treating water, washing soda plays a vital role due to its chemical properties and ease of use. Now let's take a look at plaster of Paris, which is quite a versatile material. It's used for making toys, decorative materials, and even for smoothing surfaces. You might not realize it, but it also plays a vital role in the medical field. Doctors use it to support fractured bones and help them heal properly. So how is it made? Well, the chemical formula is Ca-SO4H2O, which is calcium sulfate hemihydrate. It's produced by heating gypsum at about 373 Kelvin or 100 degrees Celsius to remove water and form this powder. When mixed with water, it quickly sets into a hard substance, making it ideal for casts and molds. Its ability to harden fast and support structures makes it really valuable in various applications. Overall, plaster of Paris combines chemical properties and practical uses, connecting science with everyday needs, whether in art, decoration, or healthcare.